So that's one way. At the very last equation that I wrote last time in the last lecture, the addition of electrophiles to 1,3-dienes. And it's important to appreciate a 1,3-diene. The double bonds these are conjugated, because the double bonds, all the pi orbitals in this system are adjacent to each other, so you can imagine the electrons in the p orbitals all being interconnected. This is one functional group. This is not two double bonds. It's a 1,3-diene. So you can imagine here, if everything is in the same plane, you will have 4 electrons in that. And the electron density is, if this is one functional group, not two double bonds. And you should appreciate that that's one functional group. That's very, very different. It's really very, very different compared to that system, which is simply two isolated pi bonds. This kind of molecule, the two double bonds react independently of each other. One reacts and then the other, whereas here this is as I say, a simple one functional group. Nothing ever happens to this double bond without this one knowing what the hell's going on, and vice versa. So it's important to recognize that these two systems are really very, very different. So we have two ways of forming the double bonds, or the allocation, sorry. The worst thing about this approach is that when you stand here and you can hardly see anything. It's like you're going from bright sunlight into a dark room. But we'll somehow manage. Okay? So let's look at some results now for the second one. And the results are really the same for the first one, as you will see. Some chemistry. If you take this compound, 1,3-butadiene plus HBr, you do the reaction at minus 80 degrees, you get two products. In an 80 to 20 ratio. If you do the same reaction at 40 degrees, plus 40, you get the same product, but in a 20 to 80 ratio. Now, the other piece of information that is useful to have, if you take either product take this product pure and you dissolve it in the presence of a little bit of excess HBr at 40 degrees, you get a 20 to 80 mixture. And if you start off with this product under the same condition as 40 degrees, you also get a 20 to 80 mixture. So how do you explain this? And I'll give the conclusion first, and then I'll show you the obvious way that it arises at the conclusion. At minus 80 degrees, the product ratio represents the kinetic ratio. In other words, the reaction takes place and nothing happens afterwards. At 40 degrees, the products are in equilibrium. And so the ratio reflects their thermodynamic stability. Okay? That's the conclusion you draw. What I'd like to do is just to go through it again. Try to see if you can recognize from some of the things you might remember from last year why this product, how could you actually make a guess that this product should be thermodynamically more stable than that? What basis do we, is it something that you have to be told, or can you make an educated guess about that? And I think you can. So let's just do a little bit of the chemistry to make sure that everybody's very comfortable with this thermodynamic and kinetic ratio. So let's look at the kinetic product. So that's the product that's formed, and there is no interconversion at minus 80 degrees between the various products. So what's happening? At minus 80 degrees, we form the allyl cation. And over this system, there is in fact overall a positive charge, as we said before. The methyl group is electron donating, so we expect a higher charge density here, a higher positive charge, a higher partial positive charge if you want. And the negatively charged bromide ion, I have it. Thought I had a green one here somewhere, but the negatively